is here at UCLA.
Okay, so
David, yes.
Okay, so I'll be talking about statistical approaches for biomarker research, and many of you are not doing biomarker research. Many of you are doing mobile health technologies and mobile sensing, but as I hope you'll see as we go through, a lot of the same problems that we've run into in molecular type biomarkers are really analogous to the things that we have to deal with in mobile health. We produce lots of data, and we want to make a scientific conclusion on the basis of that data. Okay. So my background is that I've worked on statistical methods for analysis of high-throughput genomic and proteomic studies. Earlier in my career, I spent a lot of time sort of more algorithm development, data analysis methodologies, and the challenge was that despite what hopefully was a good statistical analysis plan, the studies wouldn't really amount to anything. We'd spend a lot of time with a lot of analysis, but often we failed due to the study design, that a poor study design will produce poor results even with the best methods that you can deploy. So a lot of what I'll talk about is what are some of the considerations in terms of study design that we need to think about to be successful in sort of a big data research world, whether it's molecular markers, activity monitoring, or sensing technology that's going to produce a lot of data. So I'll just mention a few quick terms. Hopefully everyone is familiar with these things. But whenever we are trying to evaluate the utility of a biomarker or any method for predicting an outcome, say cancer status, yes or no, whether somebody has any particular disease or not, there's a couple of factors that we should consider. The first is the sensitivity. So the sensitivity is the probability of testing positive that from the biomarker or the biomarker panel among those who actually have disease. So this would be the true positive rate of a biomarker test. The specificity is the probability of testing negative among those with no disease. 1 minus specificity is the false positive rate. And we also sometimes see the accuracy, which is the probability of a correct diagnosis or a correct decision. The accuracy is something I will generally recommend people not to use as a metric of the utility of a biomarker model, because the accuracy really depends so heavily on the prevalence of the population. If you have 1% of the population who have a disease and you want to do a screening test, and your screening test said, well, everybody does not have disease, well, you're accurate 99% of the time, but it's completely useless. Okay, so I'm going to take a sort of a large-scale view of study design. So this is from this is sort of the stages of biomarker study design, stages 1 through 5. This is from a paper in 2001 by Margaret Pepe, who's done a lot of work on study design considerations for biomarker models. The sort of the ones that we're actually typically going to be interested in for academic style projects are really probably phases 1 through 3. Phase 1 will be essentially to do our discovery study. These would often be case control studies where we have a relatively convenient sample of subjects to identify promising directions. The phase 2 is the clinical assay development and validation to determine if we can use the assay to detect established disease. And the third stage is the retrospective longitudinal stage, where we might enroll patients without necessarily knowing their disease status, measure our biomarkers, and then as we go through the study, the subjects will reveal themselves whether they're a case control, and this is often called a nested case control study. The steps 4 and 5 are typically often beyond the scope of an academic project. So the phase 1 study will either utilize molecular, clinical, imaging, or sensor-based technologies. And the reason that they often fail is that they're often case-controlled designs of really sort of a bad nature. They're case-controlled designs where you might have subjects with cancer, and then the control subjects are the people who run the slowest in the lab. You get healthy people who, anyone can tell the difference between an older cancer patient and a young, slow lab tech. But often the studies are testing sort of these essentially useless comparisons and developing markers in a sort of a useless setting. In often early phase discovery studies, covariates or other prognostic variables are considered, or sometimes not. Subjects are matched. And often the failure point is at this early phase where the discovery setting doesn't match the intended clinical population. I'll talk more about that as I go along. Sort of to address this often systematic failure of biomarker studies to identify clinically useful markers, the Early Detection Research Network at the NCI has developed a set of study design considerations that sort of incorporates 4 different components to consider when putting together a biomarker development and validation study. So those 4 are the clinical context, the performance criteria, the biomarker test itself, and the sample size. Okay. So the first element is the clinical context, and typically what we're interested, the central question really is for what population and in what clinical setting is the biomarker intended. So really at the very beginning, try and identify where this is going to be. If we want to develop a test for lung cancer, just looking at people with lung cancer and people without lung cancer may not yield any sort of useful comparison. People without lung cancer, younger, maybe not smokers, and you're not going to really gain any information that would be applicable to any clinical diagnostic setting. The study population, to produce something useful, we really want to have the study population sort of match the clinical application. We want a lung cancer detection study, maybe looking at people who are high-risk smokers and have, say, an incidental finding on a CT exam. That might be a population where we could say, well, a biomarker to determine without doing additional surgery whether that subject has cancer or not might actually be useful and really represents the population for which you're trying to really make a clinical decision. Ideally, we want our study population to be a random selection from a prospectively collected cohort with outcome blinding. We also have to consider the issue of confounding. So confounding is when cases and controls differ on factors that are related to the biomarker and that are potentially also related to the stage to the disease. So this could be, for example, smoking status, age, and ethnicity. And if we ignore these factors in our study design, we can potentially build a marker that detects whether someone's older or younger, but not whether they actually have disease. Standard study designs, standard observational study designs usually try and handle the confounding issue through subject matching. So we match subjects with particular demographic or predictive characteristics versus we match cases and controls with the same set of characteristics. The challenge with that traditional approach is that then we often will render the study population non-representative of the actual clinical population that we're trying to make a decision about. And in the worst case scenario, what we can end up with is a biomarker test that's useful sort of in a comparative sense, that if you have a case and you have a control, you can maybe tell the difference between the case and control and say which one has cancer. But that's not how a clinical decision-making needs to be done. We need to have a subject in front of us and then make a decision about that subject, not say, is this, relatively speaking, how does this person compare to another person? With subject matching, we also remove the ability to assess the combined predictive effects of biomarkers and covariates. So we have to consider demographic and confounding characteristics, but potentially matching on those characteristics can be very troublesome for creation of an eventual predictive biomarker study. Next are the performance characteristics. So, there's sort of we have performance characteristics like the true positive and true and false positive rate, but often we don't want to really view these in a vacuum. The performance characteristics that are actually necessary may really depend on the clinical context of the biomarker test that we're trying to construct, and just having a high sensitivity or a high specificity in the absence of sort of understanding the clinical context may not produce something that's actually very useful. So in the study design phase, we often want to think about what are the minimal acceptable levels of the true positive and false positive rates, and those will depend on, potentially what are the existing methodologies. We want to build something that improves on an existing method, maybe in the true positive or maybe in the false positive rate. May depend on whether we're in a sort of a diagnostic setting where high sensitivity is important, or a screening setting where high specificity is important. It also may depend on the error consequences. So if we have a false negative in a sort of a clinical workflow, that may create a huge problem for the patient. The other thing is cost. For how much sort of added value for an increase in a particular level of sensitivity or specificity is going to cost. So the biomarker test itself, and I'm keeping this in the context of biomarker, but this can be any predictive model really, whether it's specific molecular markers or whether it's features that we can detect from a smartphone sensor. So the ideal setting for the biomarker test, not the individual biomarkers, but the sort of the combination of markers to create a model or a decision rule for evaluating whether somebody is likely to be a case or likely to be a control, is we need to have blinded assaying of the samples or blinded assessment of the samples. The biomarker test ideally should be a combination of new things that we can measure and existing graphic factors that we have in our study. So often the simple clinical and demographic factors can get pretty far in terms of a prediction, and often we're trying to add value over and above what is really simple to already measure and what's already sort of free to measure. The ideal case is that the biomarker test will utilize a predefined algorithm and combine quantitative factors, where critically the algorithm development and the algorithm assessment should be separate. One of the sort of the larger problems of a lot of early biomarker models is people would measure 10,000 genes. You would create the best model you could on those 10,000 genes, and then say, well, look, it has 99% sensitivity and 99% specificity. It's a great model. Well, when you have lots of markers to choose from, you can create a great model, regardless of whether there's actually any association between the factors of interest and the outcome of interest. So what we really want to do is build a model and then test the model on independent samples is the ideal case. I'll get into validation as we go through this. Okay. So next talk about some of the statistical approaches to building a biomarker model or a predictive model of any sort. And I like to sort of classify them into sort of two bins that are really based on the philosophy of what we're really trying to achieve with the models. The first philosophical approach is to create a model with a relatively small number of factors which we can individually assess within the model. This is sort of more sort of classical statistics, classical sort of predictive models in medicine, where we're often very interested in making individual conclusions about each of the factors we're looking at, and to really understand how each one of those individual factors is contributing to the eventual decision-making of the model. The second philosophical approach is sort of what I'll call a profile model. That's the term I used to use. It's probably more the term that everyone else is familiar with is machine learning, where you're creating a model potentially with a relatively large number of factors, and where the individual assessment of the contributions of each of one of those factors is not necessarily important. The importance is the ability of that model to predict an outcome that we care about. So the first approach, the models where we want to have a relatively small number of markers and individually assess them, the first step often in the study design is really to reduce the problem down to something that you can actually use those kind of models. So often when I'll design a study, the very first step will be an initial discovery set where the objective is not necessarily to build a model and make any specific conclusions, but to reduce down the dimension of the problem and identify maybe 20, 50, 100 promising features or markers that we can then build a model with in another sample set. Often the way we prioritize the markers depends on a number of different features. There's sort of standard statistical significance. Look at the p-value. If it's a two-sample test, we can compare the expression of a particular marker between our cases and controls using a t-test. But that's often not really sufficient to really identify what we want. Other things that we might want to consider are the actual magnitude of the difference. Now, some of that's going to be in a t-test is going to be partially include the actual magnitude of the difference, but we also potentially consider the classification ability. So, looking at say, the area under an RSC curve to identify how well the individual factor discriminates cases versus controls. Another feature is the uniqueness. So, with biomarkers, with imaging factors, with sensor data, a lot of the features we're going to collect are going to be relatively highly correlated with each other. So if we, say, chose the 50 markers with the smallest p-values, those 50 markers may all be essentially telling us the exact same piece of information. They may, if it's sort of molecular markers, they may be all in the same biological pathway, and once you measure one, you sort of know the information content that you would get with all the other ones. So assessing the correlation of your top factors and not focusing all of your follow-up work on a whole set of markers that are basically only telling you one piece of information. This one piece of guidance, as many of these pieces of guidance, I've sort of appreciated the hard way, where we did some of our discovery work. We found what the markers that had the smallest p-values, had the largest area in the RSC curve, then went for a validation study and found that there was only value in any one of them. Any one of them was decent, but there was no value in measuring 10 markers. They all had the exact same information content. So typically within sort of the overall approach one, after we do our initial discovery, after we reduce down a marker set to a more manageable number, then the next goal will be to have a follow-up study where we can then validate those individual targets in an independent sample set, and then construct a multi-marker model, where the construction of the multi-marker model is going to be done when we're only assaying those 20 to 50 markers, so that the model building is not so heavily influenced by selection bias, where if we're looking at 10,000 markers, it's going to be often very hard to tell whether the model looks good because we're measuring some true biological signal, or just because we have a lot of noise. Importantly, for this phase, as I had mentioned before, it's always valuable to include clinical and demographic factors. You want to make sure that your biomarkers are measuring something of the true biology, not just recapitulating the effect of, say, age on the risk of a particular disease. Okay, so the second philosophical approach that I mentioned, sort of these multi-marker models where we're not as much interested in the individual prediction ability. Using the discovery set, we potentially will identify a very large number of features that are useful. We're not necessarily 20 or 50, it could be 100, it could be 500. And we then can create a sort of a profile model on those set of features. And then the key thing will be then validating the performance of that model on a completely independent set of samples. There's lots of different types of models. I have a very limited list here. I'm sure in the room there's 20, you can name 20 other sort of machine learning predictive models and that are out there. But in my experience, spending a lot of time worrying about which exact type of model to use is not really time necessarily well spent. And maybe I'm going to do this slide and go back to the last one. There's no model that really is the best, and trying to decide what the best model is often not a sort of a good use of your time. You can, if the statistical and bioinformatics literature is full of lots of articles which say, I've developed a new method, and look, my new method is better than all the other ones, and they show simulation studies or things like that, which seem to show that their method is better. And there's lots and lots of these papers, and so then you start to wonder, well, each one of these individual things looks the best in its own paper, but how can that can't possibly be in a general sense? My general guidance is that the sort of the best predictor of success for when you're working with models is that the more you understand what the model is doing, the more you understand the assumptions that go into the model, the more you understand the structure of your data, and try and find a model that actually fits the structure of your data and the potential problems. That's probably going to be the best model. Where there's alignment between the assumptions that are going into it and the actual data set that you're using. So, I think one of I would say probably the most important thing in successful model construction is really understanding your data, looking at your data, looking at missing data, looking for outliers, seeing if there's inconsistency in how variables are coded between subjects, or inconsistency between how data was collected, really understanding the measurement scale of your variables. And also looking at the relationships between your variables, trying to force variables into models that are essentially telling the same information can often yield extremely confusing results. My overall, what I feel is that there's lots of good machine learning techniques, but the algorithms don't think, and algorithms don't understand the data and what all the eccentricities that have gone into the data collection. And so assuming that an algorithm will, in some sense, compensate for the peculiarities of the data is sort of a path to developing something that's not going to be very useful. So, my general advice is, don't worry about the model, understand your data, and then find a model that is appropriate for the structure of the data that you have, rather than trying to get something that seems like the new hottest technique. Sort of once we've actually created a model and created sort of decision rules, as I mentioned, the things that we'll want to end up with are things like the true positive rate, the false positive rate, the area under the RST curve. But to get these things, this really needs to be done in a validation study. So validation. So the reason that we need validation is, as I mentioned, one of the key ones is marker selection bias. So if you have a large number of markers and you create a model, you're going to be able to create a model that looks really good. One of the research projects that I did with one of the other statisticians in my group is we did a simulation study to see, well, if you're allowed to choose from 100 markers and you have, say, 50 cases and controls, what would you expect the area under the RC curve to be if those markers are just random noise? Well, a sort of a not thinking about it too hard, you say, well, if you just generate a bunch of random noise and put them all into model, you should expect to see nothing, right? They shouldn't be able to predict the true disease status of your subjects at all. But just through random chance, some of the variables will be related to the outcome, and the expected area under the RC curve is not 0.5, it's not 0.6, it's not 0.7, it's about 0.8. Something like that. So now, you sort of say, well, how can that possibly be? It's because you have a lot of things to choose from, and prediction models will extract all of the information that potentially is in the variables, even if that information is just random noise and this has chance associations with the outcome. So the ultimate thing is, if you put a lot of variables into a model, the model will look good. And so that's why we need validation, because if we want to really know how well any model performs, we need to separate out the sort of variable selection and the actual evaluation of those models. Somewhat of a smaller effect, but it's also there, is that we also have potential overfitting of the relative weighting of the individual variables in the model. So this is particularly the case with smaller sample sizes, but when you do a model building process, it'll fit the optimal weighting, and if that optimal weighting may work very well in the initial model building step, but may not really be very generalizable to a larger population. So in order to evaluate that, we really need to go to a validation set. So some of the basic validation strategies that people will often use is there's the cross-validation techniques, where leave one out cross-validation, or more generally k-fold cross-validation. These, if you don't have an independent set, this will give you somewhat of an idea about what the sort of actual information content for the variables that you're putting into the model are. Alternatively, we can divide our sample using a test training design, or ideally, the best case scenario is a totally independent sample. I'm going to skip the leave one out. So for k-fold cross-validation in general, we divide the data set into k separate groups and leave out one group at a time. Within the k-1 groups that are left, we reconstruct the model, and on the basis of that final model, then make predictions about the status of the left out cases. So this k could be 5, it could be 10. The 5 and 10 are probably the most common types of cross-validation that we'll see. Instead of doing any specifically dividing, we could just, in principle, say 10-fold cross-validation, remove 10% of our cases. We run the model selection, model fitting process on the 90% of subjects left, and see how well they predict the remaining subjects. This can be very useful for evaluating whether there's any real information content in your variable set. If you get relatively low accuracy on your cross-validation, it's likely that the variables you're measuring are not particularly predictive of the outcome, even if on the sort of initial construction model, it may actually look pretty strong. What I will typically propose for grant proposals where the objective is to construct a predictive model is to have a training test design. So this is where we will take the overall sample and we will divide it up into a model building cohort and a model testing cohort. Typically, the allocation ratio is maybe 2/3 into the training set and 1/3 into the test set. Then we perform the marker selection and the model building within the training set. We compute all the model-based parameters. But then when we want to look at sort of the utility of the model, all of those are computed only on the test set. So we sort of lock down the algorithm on the training set, apply it directly to the test set subjects, and then we can compute the area under the curve, the sensitivity and specificity, and things like that. One thing that's critical for success of the training test designs is to first, one thing that's often useful is to do a random selection. So we don't necessarily want to put all the subjects that were collected at site A into one group and the subjects that were collected at site B from another group. Ideally, we should have a random selection, but we also want to maintain balance across the groups. So if we have 30% cases and 70% controls, ideally we'd like to maintain that ratio within both the training and the test groups. So we often do a stratified randomization to construct our training and test groups. An important reason for that is that then we often can maintain sort of the appropriate calibration between the training and the test groups, particularly since we'll sort of, if we want to interpret a sort of a model-based score, it'll be much easier if we sort of have the same interpretation within the training and the test groups. Okay. So for an independent sample validation, this is often considered to be the gold standard. The challenge for research study is that if we are going to a completely independent population, those populations may really differ in terms of, say, response rate or disease rate. They may differ quite a bit in terms of the demographic characteristics. Hopefully they don't differ in the collection methodology, but that's one of my studies unfortunately failed that way, where the two sets had they used different collection tubes for some reason, and those collection tubes had an influence on the biomarker levels, and it did not work at all well. Okay. So, you know, when we're considering the potential utility of a biomarker model, we always have to also consider the fact that there's often pre-existing models that are out there for making, say, clinical decisions, and often the goal will be to be able to demonstrate at the end of our study that we can actually do better than those models. But in order to do that, we have to be able to include those factors in the model and see what really measure the added value of our new things over and above what has been previously done. So often a measure of success is the differential AUC, the AUC of the combined model versus the AUC of the model without the new biomarkers of interest. Okay. So the next topic is the sample size. So why do we do a sample size calculation? And the usual response is because the NIH reviewers make us do that.
Correct.
I like to think that there can be some value in addition to satisfying an NIH review panel. And the reason that from a statistical viewpoint, I think it's very important to consider is to avoid wasting your time and money. Many of you are junior faculty, and you cannot, and can be incredibly costly to waste not only money, but more importantly, your time. So the two sides of this are you want to embark on a study that has a reasonable probability of success rather than one that doesn't. And so a sample size calculation can help you really evaluate what your likelihood of success is for your study. So in order to perform a sample size calculation, what are sort of the basic sort of laundry list of items that you'll need to know? The first thing is, what is the study endpoint? that seems like a simple thing, but that actually can be one of the most challenging things. And certainly, when in my group, we have debated quite a bit about what the exact structure of the endpoint that we'll use. But without knowing the endpoint, we can't really do a proper power calculation. Once we have the study endpoint, then we need to be able to estimate many different things. So the first is, what is the effect of the intervention or the magnitude of the relationship? Now this is hard, because if you knew what that was, you wouldn't need to do the study. So what's often required here is good guesses, is understanding of the prior literature in terms of the magnitude of other things, the effects of other interventions. Hopefully pilot data, that's the best case scenario. But that's one of the hardest things for performing a good power calculation. Second is, how much variability is there in the outcome of interest? If what we're using has been measured previously, this can often be found in prior literature for pilot study. What is the level of power we're hoping to achieve? So if this is an NH grant, that's relatively simple. It's at least 80%. Next, we need to know if we're using a one-sided or two-sided test. This is also relatively easy. In most cases, we're interested in doing a one-sided test. If you're doing early phase clinical trials, a one-sided test may be the appropriate scenario. But for generally, there sort of needs to be a good reason for that. Next is, what is the statistical test that we're going to use to compute power? So this is where a consultation with a statistician can be useful to really evaluate what's the appropriate way that the analysis is going to be done. And then, of course, what's the overall design? So a couple of additional things that we often want to consider. One is accounting for study dropouts. So when we do our sample size calculation, accounting for the fact that if you're measuring people, if you're evaluating people over time, you will have incomplete data. You will have people drop out. You will, and so getting some idea of that ahead of time is important for the sample size calculation. Also accounting for multiple comparisons. So if you're going to have not just one endpoint, but many things that you're going to be measuring about the subjects, if we want to make sort of legitimate conclusions about them, we need to adjust for the fact that we're doing multiple testing, and that needs to be incorporated into our sample size calculation. So some of the ways that I see the sample size calculations often failing in a grant application is if they don't use the preliminary data. So if you have preliminary data, it should really inform your sample size calculation. It shouldn't be separate. Other ones where I see is where the sample size calculation doesn't use the planned statistical methods. So there should be strong alignment between the analysis plan and the sample size calculation. So another is I see where the prediction modeling doesn't. We have a very large number of predictors relative to the sample size. This is often not incorporated directly into a sample size calculation, but is something that will often get fairly criticized by the panel. So I'm going to give you a few bad examples and then maybe a good example. So some of the bad examples, the first bad example is the previous study had 150 subjects and it was significant, so therefore that's a good enough sample size for us. So unfortunately, this isn't mathematically true, and that prior study may have been very different in a lot of different ways, and so the prior sample size is not a basis for choosing. The second one, I do a lot of basic science studies, and I see a lot of we have 10 mice per group because we have 10 mice per group. Well, that may be exactly the right number, or it may be completely wrong, but we should know before we start an experiment whether it's something that's likely to be successful or not. Next one is sample size calculations are not provided because there's no prior information on which to base them. And often that's kind of true. You're in a situation where you're a little bit in the dark about what exactly you might expect to see in your study, but that doesn't remove the requirement to have thought through your research design and what possible effects are going to be, and to at least give the reviewers some chance to assess that. The next one is just about sort of sample availability, and this is really important to really show a review panel that you have. You actually have access to the patient population and ability to recruit them, but it's also not a justification for why that's the sample size. And the sort of power by assertion, I've started with editing grant applications where somebody has put my name right there and said, David Elashoff said that the power was 80%. And unfortunately, that doesn't, not very convincing. So in the last minute that I have, I'll give you an example of a good power calculation. And it's not good because there's any science behind this particular one, but this includes all of the necessary information for which you need to justify what your sample size is. So our sample size of 38 in each group. So telling people exactly what number, don't give a range, give a specific number, will be sufficient to detect a difference of 5 points. So 5 points is the magnitude of the intervention effect that we are assuming on the Beck scale of suicidal ideation. Now we have our outcome variable. We've stated it clearly in the power calculation. Assuming a standard deviation of 7.7 points, the level of variability, we have that there. What power is that going to achieve? 80%. We have a two-sided significance level of 5%, so the alpha level of our test is 5%, two-sided test. And then lastly, the statistical method we're using, a two-sample t-test. So now in one sentence, we've included every possible piece of information we really need to say how we came up with the number that we are. Then we can say this number has been increased due to potential predicted dropout. And then the hard part of sample size calculation comes in. How do we justify why 5 points is the expected magnitude of the effect? And that could be based on literature, that could be based on pilot data, but that's where you need justification. And the standard deviation, why that number is there. Every time I look, we're going to be a little more close. Okay, so I will stop right there.